Well, this example, it's not going to be a subspace, but in this example, both the first and the third criteria of the subspace theorem, they are satisfied. Zero vector belongs to this S. Zero vector belongs to this S, and if you have a vector which is in S, then by scaling this vector, you will end up with the vector in S as well. You have to prove this, of course, but that is true statement. So this is the very interesting example which fails. It's not a subspace. I'll show you it fails the second criterion, the being closed on the addition, but the other two, they are satisfied. So it's a really like a elaborate, quite sophisticated example actually, chosen specifically to show you, but there are examples where both zero and scaling is satisfied, but addition is not satisfied. The other reason I chose this example is that you can take this S and you can rewrite it slightly. You can rewrite it like so. You can say S is the collection. It is this subspace. You see where I took only the first condition, and then I took the union, set union, with the set like so. Each of these sets individually, this set individually, and this set individually, they are subspaces. These are the examples of the orthogonal complement subspaces. So my S, it's the union of two subspaces. Union of two orthogonal complement subspaces. Here it is. One orthogonal complement subspace, coefficients 2, 3, negative 4 from here. Union, the other orthogonal complement subspace. If you remember, we had this intersection lemma, which said that if you intersect things here, the result will be a subspace. It turns out, when you take the union, this is no longer true. When you unite subspaces, you may end up with non-subspace. And in fact, there is a question in the yellow book which asks exactly that. It says, find a counterexample of two subspaces such that the union of those subspaces is not a subspace. You can reference to question 21 as a counterexample when we finish with that question. Which exactly that question, I don't remember. I think it's either 35 or 36. That's the one about the union. So what do I say? I will make some abbreviations. I'll call this S1. I will call this S2, just to lighten up my writing a little bit. So this will be S1, this will be S2. Here's my counterexample. Look at this. Basically, the idea behind the counterexample, it's pretty random. I chose the vectors pretty randomly, but I chose it in a way that one of them satisfies exactly this, and the other one satisfies exactly this. And I was hoping that if I add them up, the sum of these two, it will satisfy neither of these two. And here's the example. Look at this. First vector x is like so, 2, 0, 1. I claim that this is a vector which is subject to this condition. 4 plus 0 take 4 is 0. So my vector is in S1, and that's why it is in S, which is union of S1 and S2. For the second vector, I choose 1, 2, 0, which is a subject to this condition alone. 4 take 4, 0. This is a vector in S2, and by implication in S as well. Now, if I add them up, it will be the vector 3, 2, 1. And let's just test this. If I test this 3, 2, 1 against this condition, or against this condition, fails, right? It's 6 plus 6 take 4 is not 0. So x plus y is not an S1. If I test my vector against this condition, it will be 12 take 4 plus 3. Again, it is not 0. So my vector x plus y is not in S2. And that's why vector x plus y is not in the union.